Hi everyone. Thank you for joining us today to hear Mahmood and I talk about this permanent magnet motor design webinar series. We will be discussing how to optimize the BLDC motor's magnet size, where these motors are frequently used, and watch few simulations using MotorWizard software developed by our company Electromagnetic Works or EM Works. Firstly, let me introduce ourselves. My name is Cal, and I work as an account manager in EM Works company. I primarily handle commercial sales for the company, and my colleague Mahmood is the senior product manager for MotorWizard product, and he is involved in this product development. He will also be doing the technical presentation using the MotorWizard product today. Feel free to write down our details to email us afterwards for any inquiries. So our agenda for today is following. I will briefly talk about our company, EM Works, the products we offer, and the different tiers of our licensing structure. Then I will talk about the different industries where BLDC motors are utilized. After that, my colleague Mahmood will do the technical presentation. And at the end of this presentation, we'll take a look at various learning resources available by EMWorks. So our company EMWorks, we develop and sell 3D and 2D electromagnetic design and simulation software. Our products are primarily available as an add-in tool for SolidWorks, and we also offer our solution inside Autodesk Inventor 3D CAD. We offer 4 products which covers a wide range of applications. Let's take a look at each product. Our first flagship product is called EMS, which can be used for electric and magnetic field modeling for low frequency applications. It can design and simulate various applications, including solenoids, motors, transformers, permanent magnets, bus bars, insulators, wireless charging devices, etc. Our second flagship product is called HF Works, which can be used for electromagnetic simulation of RF, microwave, high frequency and high speed electrical and electronic devices. It covers applications like antennas, waveguides, filters, resonators, connectors, etc. Our third product is called EMWorks 2D, which currently offers 2D static analysis of planar and axisymmetric geometries. The latest addition in our suite of electromagnetic simulation software is called MotorWizard, which will be the topic of our presentation today. It is a 2D template-based motor design software, which currently offers analytical and finite element analysis of BLDC motors. We also offer few multiphysics options, which can be added on top of these softwares like motion analysis, thermal analysis, linear statics, and circuit analysis. Moving on to the licensing structure, we offer 2 tiers of programs. Commercial program where you can use our software for commercial activities. Then we also offer academic program, and under academic program we offer student license, research license, instructor license, and campus solution. The topic of our today's webinar is how to optimize magnet size for brushless DC motors. This webinar is a part 2 of our permanent magnet motor design webinar series. Part 1 of this webinar series took place on May 11th, and its recording is available on EMWorks webpage. At the end of this presentation, I will also announce the topic for part 3 of this webinar series, so stay tuned. Before we go into the technical presentations, let us quickly see the industries where BLDC motors are frequently used. BLDC motors are used in healthcare industry for sleep apnea equipment. They are also used in portable ventilators, which is extremely helpful in case of patient transfers. They are also used in other medical equipments like dental drills, dispensers, MRI machines, etc. The use of BLDC motors in automotive industry is very well known. They are used in electrical vehicles for its precision control, efficiency, anti-sparking technology. They are used in various other components like windshield wipers, windows, music systems, etc. BLDC motors are also used in aerospace industry. They have been used by NASA for outer space missions, as these motors are resistant to wear and breakage and have the ability to survive harsh conditions. They are also actively used in industrial machines like linear motors, servo motors, industrial robots, and drive motors. BLDC motors are also a popular choice for consumer electronic products like printing machines, vacuum cleaners, and HVAC systems. Now let us move to the technical presentation. However, before we move on, I would like to mention few quick points. To avoid any background noise, kindly mute your microphones. Use the GoToMeeting chat window to type in your questions, to which we will answer at the end of this technical presentation. And a webinar recording will be sent to all the registrants in a couple of days. Now, I would like to invite my colleague, Dr. Mahmood, to deliver this presentation he has prepared on permanent magnet motor design. Thank you, Mahmood.
Thank you very much, Cal. Can you just share my screen? So I hope everybody is seeing my screen right now.
Yes, Mahmood, go ahead.
Okay. Hello, everybody. I'm Mahmoud Bijan, and thank you for joining this webinar. As my colleague mentioned, and you can see here, the title of this webinar is How to Optimize Magnet Size for BLDC Motor in SOLIDWORKS. This is the second webinar of a series of courses regarding permanent magnet motor design. This webinar was initially supposed to cover both the BLDC motor and PMSM, but due to the amount of material provided in this webinar, we decided to present the part related to PMSM in another webinar. Next webinar is completely about PMSM and will be about how to generate sinusoidal back EMF in permanent magnet motors. So stay in touch, and we will announce the date and description very soon. I'm going to start the presentation right now. If you have any question, you can write at the message section, and I will try to answer as much as possible. You may ask a question at the end of the presentation. Okay. So the agenda of this webinar is as follows. First, an introduction about permanent magnet motors will be provided. Then the general process of designing permanent magnet motors will be presented. In the next step, we will use MotorWizard to create the model of permanent magnet, and the result of simulation with different studies will be conducted. Then we will analyze and study the results, and we will discuss them to get some conclusion, and at the end we can answer the question. Okay, let's start the presentation with this question. What is permanent magnet motor? Okay, permanent magnet motor refers to the machines that permanent magnet is used in their structure, either in rotor or stator, or even in both structure. Okay, any type of machine which has the permanent magnet motor can be called permanent magnet motor. Okay, but what is the advantage of using permanent magnet in electrical machines? Using permanent magnet can increase the torque density and efficiency of the machine, and moreover, the starting torque of the permanent magnet machines can be higher than the other machines, like comparing switch reluctance or induction machine. So you can see that it's quite a good advantage using the permanent magnet. One more interesting advantage of using permanent magnet is that the diversity of the configuration that can be developed by shaping and placing the magnet is very high. You can see just a 3 example of these permanent magnet motors. It's just a simple one. We have quite pretty more than 20 types of the motor. You can just need to play with the magnet shape or forming or how to put them next to each other, and you can build a new motor. And each new motor can give you the new performance, and you, based on your application, you can choose which one is fitting to your application. Permanent magnet motors can be used with both DC and AC supplies. Okay. In case of the DC supply, in case of using DC supply, it is called brushless DC motor, and in case of using sinusoidal supply, which is the common type of the supply in the industry, it is called PMSM. Since brushless DC motors are supplied with the DC voltage source, the voltage is applied in form of the pulses to the phases. Therefore, a simple control can be used, but commutation of the current in the phases generate extra torque ripple. PMSM needs a 3-phase sinusoidal waveform for its operation, which needs complex control system. The torque ripple due to the current commutation are eliminated in this machine, but that doesn't mean torque ripple is zero. It provides higher performance with the higher cost. As I mentioned before, the focus of this presentation is on BLDC motor operation. Since the structure of 2 types of the machines are same, some of the conclusion can be extended for PMSM motor. Okay. The design process of the, we talked about design process of the permanent magnet machine in previous webinars. I'm gonna little quickly talk about it here. When we want to design the machine, we start with the number of poles and stator slots, and we decide about the winding configuration. Then we choose the material. By having these data, we make the main dimensions. Main dimensions here means the rotor outer diameter and stack length of the machine. Could you please mute your microphone, please, to be able to other people hear very well? Please mute your microphone. Thank you very much. After that, after determining the main dimensions, we have to decide what is the air gap length, and then we choose what type of the rotor structure we want to have as a desired motor, and we go with for magnet sizing, which is important part of the rotor structure. After that, we will have the number of turns and conductor size, which is based on the equation and normally vacuum of equation. And then we decide a slot type, stator slot type. It can be the round shape or it can be trapezoidal shape. There are different types, and each one has its own advantage and disadvantage. Finally, we come with the stator and rotor loop thickness based on the material, based on the electromagnetic property of the material. Here, it's not finished yet. If it's the first design is ready, but before finalizing the design, we have to analyze the design to see if we have reached to the desired outputs. And once if there is a problem, we have to redo this process again until we get the proper design. Okay, as you can see here, magnet sizing is part of design process. However, there is no specific formula or equation to determine the magnet size. Therefore, we are going to discuss about this part of the design. Okay. The question arises here that how we should determine the magnet size. And to answer this question, we must know which parameters are mostly affected by the magnet dimension. The objective of this presentation is to study the effect of magnet dimensions on back EMF, cogging torque, and torque profile to answer these two previous questions. So I have shortly explained these parameters in previous presentation, but for those who are not familiar with these parameters, I will explain again. Back EMF is the voltage induced in the stator winding due to the rotation of rotor magnets at certain speed. The value of back EMF directly affects the generated torque and power of the machine. And for PMSM and BLDC motor, it's tried to generate back EMF with different waveform to improve the performance of the machine. We will talk about it later in this presentation, and you will see how the magnet dimension changed the waveform and the value of the back EMF. The other parameters which might be interesting for designers is cogging torque. Cogging torque is the torque due to interaction between rotor permanent magnets and the stator piece. Cogging torque is an undesirable phenomenon which increases the torque ripple and vibration and noise of the machine. Therefore, electric machine designers try to reduce it as much as possible. At the end, we have torque, which is considered mechanical output of the machine. Although theoretically it is expected electrical machines generate a constant torque, but due to asymmetries of the machine, generated torque has some fluctuation which is called torque ripple. Later in this presentation, we will see how the magnet size can affect the torque average value and torque ripple. Before going to simulation and an analysis section, first let's get to know some useful parameters. This picture shows a 24-slot, 4-pole permanent magnet motor. The first parameter is slot pitch. The slot pitch is the distance between the center of two adjacent teeth. Its calculation is simple and is 360 divided by the number of the slot. For this machine, for example, we have 24 slot, and by dividing 360 by the 24 slot pitch for this one is 15 degrees. The next parameter is pole pitch and is the distance between the center of two adjacent and opposite magnets of the machine. Again, the calculation is simple. Dividing 360 by number of magnets gives the pole pitch, which is here is 360 divided by 4 gives us 90 degrees. These are two parameters. And about the magnet dimension, this is the surface mounted magnet motor, permanent magnet motor. We have two main dimensions for the magnets. Of course, we have the Z direction, but we don't consider this one, which is not part of design process. It's affected by something else. But here we have two main dimensions. First dimension is the magnet thickness, or sometimes called magnet length. Is the magnet length or magnet thickness is the magnet dimension in magnetization direction. To determine the magnet thickness, following these 3 points should be considered. First, the magnet can be demagnetized during loading performance and the loading performance of the machine, or when the fault happens inside the machine. Demagnetization means that the magnet loses its magnetic property partially or completely and cannot generate expected magnetic field. Therefore, you must choose the magnet thickness enough to avoid demagnetization. According to electrical machine design reference books, magnet thickness of 5 to 10 times the air gap length is a good choice to avoid demagnetization. Another point regarding magnet thickness selection is the manufacturing issue. The thickness of the magnet available in the industry varies between 2 to 3 millimeters up to the 20 millimeters, so we have to respect this limitation. At the end, cost is another issue which is a determinant factor, because recently the price of the rare earth magnet, which provides a high remnant flux density, is increasing continuously. And if you go and check, look for the price of the magnet, you can see that recently has increased significantly. We have another magnet dimension here, is the magnet span. For magnet span, story is a little different. We determine the magnet span. Of course, the cost is important, but we determine the magnet span based on the type of the application. If you have BLDC or we have PMSM operation, then it's a different story. And we have to normally shorter arcs to reduce the back EMF harmonics. Increasing it will increase the RMS value, will generate high torque. So there are a couple of things we are going to see here in this presentation, how we are going to determine the magnet span for BLDC. And here you can see that the magnet span is somewhere between 0 to the pole pitch, which in this case it was between 0 to 90 degrees. Okay, to study the effect of the magnet dimension on the machine performance, a 2HP surface mounted permanent magnet motor has been chosen. The specification of the motor are shown here in this table. The original design of the machine has like 3.5 millimeter of the magnet thickness and 70 degrees of the magnet span. There will be two studies here. First, the 3 different magnet thickness will be studied, which are 2.5, 3.5, and 4.5 millimeter. In this study, the magnet span is 70 degrees, and other specification and geometries are kept constant. In the second one, the magnet span will change from 50 to 90 degrees by steps of 10 degrees. In this study, the magnet thickness will be 3.5 millimeter for all cases. To study the machine here, we are going to use MotorWizard software, which is a template-based software to generate a CAD model of the machine inside SolidWorks and run the electromagnetic finite element analysis. I explained the workflow of MotorWizard in previous presentation, which was very simple and straightforward. However, for whom that could not attend the previous presentation, I will go through a workflow again quickly. Moreover, I will show you that what we refer when we say magnet thickness and magnet span. Let me switch to the software. As my colleague mentioned, our products is inside. It's add-ons for the SolidWorks. This is the SolidWorks environment. You can come here. See the MotorWizard is here. You can click. It will open a window here. We go for the new design. The reason that I'm going fast because I explained this one before in the previous presentation, and I hope people can back there and see how simple is it. This is that we have two main tabs: machine design simulation. The first one is for the designing the machine. The second one is for the getting the result. For example, the machine design tab has 4 sub tabs. Start with the model setting, which is here. It's a 2 HP machine, which is around 1500 watt and 2000 RPM. It has 24 slots and 8 ampere rated current. Then we go for a stator dimension. We have the type of the inner or outer runner rotor, and then we have the type of the slot. You can choose it. For example, choose this one. If you click here, you can see the dimensions and the type of the rotor or a stator you have chosen. For example, this is the slot shape, and you can, based on the, this data, you can feel here. 2.3, 9.2. If you know the number, it's very easy. Then when you put the geometry, you can come here. There is material. You can click on the material section. You can choose any type of material you want. For example, here it's M27, the steel M27 with this pH curve and other properties which is there. You do the same thing here. We have different type of the rotor shape, and it's here. The template is ready. We go with the radial magnet surface mounted, which if you click here, you will see what type of the motor you already selected. Then you can enter the values. If you want to see what is this values, again in this pictures is clear. Then we have the magnet dimensions here. You can see again the dimensions here. See, we have the magnet thickness, which is this T1 here. We put it here 3.5, and we have magnet angle, which is the same as magnet span. Is this angle that we put it here, A1. We can put 70. And then you go to the material. You can change the magnet to the radius, offset. There are other parameters you can determine, but we mainly care about these two. You came to the material, again, same as the stator one. You can choose it. For example, here we can choose this samarium cobalt magnet, which has the around 1.06 resonance. And we have the shaft material, which is here. Put something like stainless steel. Then we go to the winding section. It has automatic winding. You can choose it to be single, distributed, or concentrated. Of course, here it is not possible to concentrate it because it has 24 slot 4 pole. And then you go for the single, for example, single layer in this case, and number of the turns per coil, and the wire diameter, and the number of strands. You can choose it. In case you want to see the winding layout, you have to, sorry, I forgot to put this on 24. You have to see what is the winding structure. You can see here the phase A, coil number 1 state goes from slot 1 to 7, then 2 8. It gives you information. I talked about this thing before, and so that's the reason I'm going quickly here. Once you've finished, you can hit the validate here. When you click on validate, it's gonna show a message here, which shows that all the geometries that you have put there, it's consistent and there is no inconsistency. Once you finish, you can click on generation. Okay, it takes like around 30 seconds, 1 minute to build a model for you. The model will be shown here, but once the model is done, it's going to give us the message again at the bottom that the model is completed. I already built the model, and this is the model that I had before, the same model that I generated before. We have the in simulation section, you can choose what type of result you want. We have the performance result like torque speed, power speed, or whatever it is, and then you have the no load performance. In this case, as we mentioned before, we are interested in back EMF and the cogging tool. You can click it. You can check the boxes and then play with the options. Which speed you want to have the back EMF, or what is the number of the step you're looking for. Of course, this is the FEA result, and if you want to have the higher number of the point, a little time increases, but again, accuracy will be higher. You have inductances, which in this case we are not looking for, and we have the torque result, which is the total torque we are looking for. You can play again with the options. Once you have it, you can solve it. You can see I did it all of them in the one single tab. You can do it with this, several tabs like this one. I did it before. You can see the back EMF. This is the back EMF of the machine that we generated. And this is the flux linkage. And other result, maybe you can total torque. And this is the torque with the torque ripple, which, as we expected, has some fluctuation. And this is the cogging torque. You can see it has the average of the 0, but it has 2 peaks, one positive, one negative almost, and is symmetrical. So these are the results which easily, simply you can generate with the model. This is the model we generated right now. You can, I told you, you can come to here, check the results, and solve the simulation. Okay, I did it before for you. So here, let's back to our presentation. If you have any question about the software, we can talk about later. Let's back to our presentation here and talk about the results. Okay, I told you before that we are going to run 2 studies. Okay, the first study where we changed magnet thickness. In this study, magnet thickness will be 2.5, 3.5, and 4.5 millimeters. Here you can see that the back EMF of the machine at the rotary speed of 2000 RPM for different magnet thicknesses, it has the same shape, and the value is changing slightly. So it is, you can see that the zooming part of this section in the right figure. It is very obvious of this table. If you look at this table, that's that we almost doubled the magnet thickness from 2.5 millimeter to 4.5 millimeter, and the back EMF has been increased only by 8.3 volts. Considering the high cost of the permanent magnets in the market, especially for rare earth permanent magnet, increasing the magnet thickness is a poor action to improve machine output. If we check the cogging torque for these cases, we can realize that the effect of the magnet thickness on the cogging torque is also insignificant. It can be seen that here, that in this figure, the cogging torque has increased slightly, so not much of the change. Of course, we want to reduce it, but here it increased. It's another disadvantage. And let's go for the torque. Considering the fact that the back EMF waveform doesn't change with the magnet thickness, we can expect that the torque profile will have the same shape for different magnet thickness, and only small increase of the generated torque can be achieved by increasing the magnet thickness. This can be seen here in this figure. You can see that the average torque has increased from 6.74 to the for magnet thickness of 2.5 millimeter to 7.4 Newton meter for magnet thickness of 4.5 millimeter. This is around 10% increase, while we have increased the magnet thickness by 80%. The interesting part is that even by increasing the magnet thickness, the torque ripple is the same for all cases. Note that here we didn't talk about PMSM or BLDC. The reason is that magnet thickness does not change the back EMF waveform and the torque profile, and only change the value. Therefore, we can conclude that the magnet thickness is not a determinant factor to designing machine for PMSM or BLDC operation. The conclusion that we're getting from here, first of all, is that the magnet thickness is the parameter that we should determine based on the other factors. Considering the output that we are receiving from these machine, chain playing with the magnet thickness, it's not very significant. Okay, not increase of back EMF, increase of torque is very insignificant. Let's go to the second study. Here we are going to study the effect of the magnet span on machine performance. Let's see the results. We can start with cogging torque. Okay. This image shows the cogging torque of the machine with different magnet spans. Based on the results, two main points are presented here. First, the peak value of cogging torque, and the second, the rotor position that the peak value happens. Despite where the peak value happens, all the plots are almost same with phase differences. However, we are most interested in the peak value rather than the position that peak value happens. It can be seen from the image that the peak value is fluctuating by increasing the magnet span. For example, cogging torque for magnet span of 50 is around 0.7 Newton meter, while for the magnet span of 60 and 70 are around 0.4 and 0.8 Newton meter. To understand the nature of this fluctuation, we ran more simulation. In this simulation, we studied the 10 different magnet spans, starting from 45 degrees by this for 5 degrees up to 90 degrees. excuse me, we reached to an interesting result. And honestly, this was the first time that I saw such a result, and it was very interesting for me. If you look at this bar chart, you clearly can find a pattern here. You can find the pattern here. If you ignore the magnetic span of 90 degrees, which is equal to pole pitch, the peak value of cogging torque is repeated every 15 degrees. Increase of every 15 degrees of increase of the magnetic span. These 15 degrees, if you remember, these 15 degrees of variation is equal to one slot pitch. We talked about the slot pitch is 360 divided by the number of the slots. So the study shows that reveals that the variation of the peak value depends on the ratio of the magnetic span to slot pitch. Since the machine has 24 slots, the slot pitch of the machine is 15 degrees. Based on the result, for magnetic spans of 45, 60, and 75 degrees, where the ratio of the magnetic span to slot pitch is an integer number, like 3, 4, and 5 respectively, cogging torque has a minimum peak value, which is around 0.4 Newton meter. When the ratio of magnetic span to slot pitch is not an integer number, then the peak value will increase. For example, for magnetic span of 50, 65, and 80 degrees, where the ratios are 3.33, 4.33, and 5.33, the cogging torque peak value are around 0.69 Newton meter. And for magnetic span of 55, 70, and 85 degrees, where the ratios are 3.66, 4.66, and 5.66 respectively, the peak values are around 0.8 Newton meter. This is very interesting for me at least, and I'm sure for every designer, that they can consider very simple rule. If you have the ratio equal to integer number, you are going to have the less cogging torque, less noises, less vibration for the motor. Okay, another interesting part of this study is here. Back EMF. Back EMF of the machine at different magnetic spans are shown here, and as you can see here, what happens when you increase the magnet span? The max value of the back EMF doesn't change, but the shape is changing. The shape of the waveform is changing. You can see clearly here the back EMF waveform. The back EMF waveform for magnetic span of 50 degrees is more like a sine wave, while for magnetic span of 80 and 90 degrees, the waveform is resembling square waveform or trapezoidal waveform. So remember that I told you before that for PMSM machines, sine wave back EMF is desirable, while for BLDC motor, trapezoidal back EMF is desirable. So these figures clearly show that magnetic span is determinant design factor and should be designed based on whether we design a PMSM or BLDC motor. As I mentioned before, study related to PMSM operation will be present in the next webinar. For our purpose, which is analyzing BLDC motor, higher magnet span is preferable, because you saw that it generates the back EMF close to the trapezoidal waveform. Let's look at these figures quantitatively. As I mentioned before, and it's obvious from these figures, the maximum value of the back EMF is constant for all cases. You can see in this table. Okay, the max value for all of these five waveform is same. The max is around 100. But the RMS value of this five waveform is different. If you can see here, the magnetic span of 50 degrees has around RMS value of 67 volts, while the RMS value for the 80 degrees is 85 volts, which is quite different, at least 16 volts different. So if you focus in this figure, this bar chart, you can see that at the beginning, by increasing the magnetic span, the RMS value increases, the rate of the increase is higher when compared to the higher value of the magnetic span. Let me explain it in this way. For example, when you increase the magnetic span from 50 to 60, the RMS value goes from 66.9 to 74.5, which is around, I assume, 7.6 volts. But when you increase it from 80 to 90, it's just around 2.1 volts. So you can see here clearly that the RMS value you are receiving, it's not a big number. So doesn't mean that increasing as much as possible, it's gonna gain you that much that you expect. What this gonna affect? Where this is gonna affect? This is going to affect our performance. This RMS value is gonna affect when we have the torque. Okay, this is the torque that is generated by under the BLDC performance of the machine, this permanent magnet machine. You can clearly see that by increasing the magnet span here from 50 to 90, the average value of the torque is increasing. You can see here, for the first one is around 6, for the second one is around 7, and for the last one is around 7.5. And you can completely see here that unlike the magnet thickness here, the torque ripple profile is completely changed. Okay, so let's look at again on the numbers. Okay, these two bar charts showing the average torque and the torque ripple. You can see by increasing the magnet span, the average torque increases, which is interesting, which is something that we are looking for. And at the same time, by increasing the magnet span, the torque ripple is reducing. Again, something interesting for us. We are looking for this. Of course, this is going to be completely different for PMSM operation. We will talk, as I mentioned, next webinar. We will talk about next webinar. But for BLDC, you can realize that increasing the magnet span is a good decision to have a good performance. But there is a but here. Remember that the rate of increase at the higher size of the magnet span is not good. You can see that the difference between 80 to 90 in terms of the average value and the torque ripple, it's not that much. So if you increase the magnet size from magnet span from 80 to 90, you are increasing the cost of the manufacturing, but you are not gaining that much. Okay, let's jump to the conclusion. Regarding, we did two studies here. Okay, one about the magnet thickness, another one about the magnet span. Okay, regarding the magnet thickness, I would say that the increasing the magnet thickness to improve the machine performance in terms of the generated back EMF and torque is not a rational measure, because the effect is insignificant, and even doubling the magnet thickness is not going to improve the torque and the back EMF significantly. Therefore, by increasing the magnet thickness, you only increase the manufacturing cost of the machine. Based on the result, it can be suggested to select the minimum magnet thickness as much as possible. You know, if you go with the minimum one, go with the minimum. But you must choose the magnet thickness to avoid demagnetization during loading performance of the machine or when the fault happens. Okay, so according, as I mentioned before, and this is my advice to you, the machine design book suggests you determine the size of the magnet thickness 5 to 10 times the air gap. My suggestion is start with the 5 times, and you can optimize the size later and see if the demagnetization happens or not. This is my suggestion. Another study was about the magnet span. The magnet span, the story was completely different. It has been seen that cogging torque is related to a ratio of magnet span to slot pitch, and choosing a magnet span as a factor of slot pitch can reduce the cogging torque. It was very interesting. And second, the magnet span doesn't affect the maximum value of back EMF waveform, but it significantly affects its waveform and the RMS value. This can affect the generated torque and torque ripple. For BLDC motor design, where trapezoidal wave operation is desired, higher magnet span means higher torque and a smaller torque ripple. However, the rate of increase of torque value is slowed down at higher magnet spans. Therefore, considering the cost of the magnet, go for the maximum value. Of course, you can optimize the cost, magnet size based on the cost and the machine performance. You have to do this kind of little trade-off between the cost and electrical or electromagnetic performance. For BLDC motor, my suggestion is that it go the magnet span 80 to 90% of the pole pitch, which will result in the lower torque ripple and the higher average torque. Of course, again, if you want to do the optimization again with considering the minimum cost, you can do it. It's another story. Thank you very much for your participation and joining this webinar. I transfer the presentation to my colleague. He will continue, colleague, and then we will back to you by answering the questions.
Thank you, Mahmood.
Okay, Cal, go on.
Thank you, Mahmood. Thank you very much. So, folks, just to summarize what we learned, to do a BLDC motor design analysis, you can choose a couple of products from our suite of electromagnetic simulation software. There is one option, MotorWizard software. It currently offers finite element analysis and analytical analysis for BLDC motors. It's a 2D template-based driven software. Another option is that is our EMS magnetic package, through which you can do magnetic analysis for various types of motors, including BLDC, PMSM, or switched reluctance. Both of these options are available inside SolidWorks CAD. So feel free to reach out to us, fill the contact us form on EMWorks webpage if you would like to try the software. Let us also talk about what learning resources are available for EMWorks prospects and customers. With EMS and MotorWizard software purchase or a trial request, you will get access to demo viewer section, which gives you access to various tutorials and predefined model examples through which you can learn the software. We have some free online learning resources in the form of YouTube channel, application notes, webinars, and newsletters. All these can be accessed on or through EMWorks webpage. I would also like to invite and inform all the attendees for today's webinar that our next webinar topic in this series of permanent magnet motor design webinars will be how to generate sinusoidal back EMF in permanent magnet motors. We will let you know via emails that when this webinar will take place. You can also keep checking our EMWorks webpage for the latest updates on this upcoming webinar. Before we answer some of your questions, I would like to thank you all on behalf of EMWorks for participating in this webinar. Contact us for any product inquiries and subscribe to our social media channels for latest news on EMWorks. Once again, thank you very much.